All right, so let's go ahead and get through problem number 11 from the 2023 AMC10 B. This is just the way I go about solving this one. There's probably other methods, so you're welcome to look for other means. Suzanne went to the bank and withdrew $800. The teller gave her this amount using $20 bills, $50 bills, and $100 bills with at least one of each denomination. How many different collections of bills could Suzanne have received? So the first thing you want to do is meet the criteria. If you have, so you want to think about it, right? If you have one $20 bill, just one, and you only have 50s and hundreds after that, could you get to an even 100? No, like I can't take a 20 and like add two 50s. I'm not going to be able to get to 100 if I do that. So how many 20s would I have to have if I have to have at least one in order to end with at least exactly 100? If you're at 50, you need to add 30 and you can't make 30 with 20s, right? So then in order to have just 120, you actually have to have 5 20s. So the minimum you have to cover your bases, this is every set of data that you have, is going to be 5 20s. You're then going to need two 50s for the same reason. You cannot make it to an even $100 amount without two 50s. So you're going to have two 50s. And finally, you have to have at least one 100. After that's all checked, that's the minimum requirement. The total amount of money that you've used in your batch of 800, you've used $300. That means you need to make up $500 with whatever's remaining. At this point, I kind of just went through trial and error to kind of see what happens here, meaning let's go ahead and just make an XYZ type of chart, okay? So I'm going to say that the number of 20s, the number of 50s, and the number of hundreds. And you can make this chart in a number of different ways. You could count how many hundreds you have. I wanted to focus on the 20s. We've already met the criteria of at least one. So I could have 0 as no problem now. And these are going to be part of every single answer, every single type of collections I could have. All of these are included in all the collections we're about to do. So the first thing would be to maximize my 20s. If I have 25 20s, I have $500. Then this would be 0 and 0. Okay, now if I wanted to add some 50s or hundreds, I would have to remove $100 from the 20s. So I would have to go down to 20 because 5 20s is 100. At that point, I could maximize now my 50s. And I would have two 50s, and then I wouldn't need any hundreds. I would still have $500. In the next one, I'm going to keep the 20, but I'm going to get rid of the 50s and give myself one 100. Okay, now, are there any other sets of bills that you could have, collections, that would have 20 20s? No. Because 20 20s is $400. And you have either $100 to make up with two 50s or one 100. That's it. So now you'd have to reduce this 20. Notice the algorithmic systematic process by which I'm working. I'm not randomly making collections. I'm working down from a specific maximized point. And now I'm going to go down to this 15, and I'm going to make it all 50s. So I'm reducing the amount of 20s, but I'm going to maximize the 50s. So the 50s are now going to have to make up $200 worth. So you need 4 of them. And I minimize the 100. Then you keep the 15 the same. In order to gain a $100 bill, you have to lose two 50s. Finally, you can keep the 15, lose all the 50s, and have 200s. It's at this point you kind of want to start reasoning, meaning look for what's going on here. You've got 1 in this type. You've got 2 of this type, and you have 3 of this type. What's our guess? You're probably going to go all the way until you get to, there's going to be a set of 6 different ways. And when would the 6 different ways happen? It would happen when you get down to 0 20s. So if you're at 0 20s, we probably expect you to get, because you have a group here, right? So when you had 5 20s, it was 1. When you had 500 in 20s, you had 1. When you had 400 in 20s, you had 2. When you had 320s, you had 3. And you can see as you're going down by 5, you're gaining 1 in the number of column. So if you go down 3 groups of 5 in the 20s down to 0, so you have no 20s, we expect there to be 6. Why do we do this? To save time. We don't want to list everything out. So now if I have 0 20s, what's the maximum number of 50s I could have? Okay, you would have to have 12 50s. That's $600. I'm sorry, we want 500, so 10 50s. And you'd have to have 0 hundreds. Then you would go down to 8 50s and 1 100. And this game will be played all the way down to 0 50s and 5 100s. Why only 500? Because everything else was taken care of with the minimum coverage. So you have everything from 0 to 5. That is indeed 6. So at this point, you would be able to add the numbers from 1 to 6. You have a couple options for that. You might do the Gaussian method where you just do 1 and 6 is 7, 2 and 5 is 7, 3 and 4 is 7. You can do that and get 21, but it's such a small number, you don't necessarily have to go for the formula. The formula is the sum of the numbers, sum of integers, positive, from 1 to n. And that's equal to n times n plus 1 over 2. It's a small notebook concept. It's usually used when there's a lot bigger numbers. For 1 to 6, I mean, like I said, 7 3 7s, pretty quick. If you wanted to plug into this formula, you would get 6 times 7 over 2. Again, 21 ways to set it up. This selection over here has no impact. That's just covering the minimum criteria. That's it for this problem. I'm going to go ahead and end the video. Hope you enjoyed it. Let's get to problem 12. Okay, so let's get to 2023 AMC10 B problem 12 here, and it's also the 12B problem 6. This is going to be something you would learn in an Algebra 2 honors course, typically second semester, maybe regular Algebra 2. Your school might have different names for these subjects now. Also, it's covered in pre-calculus. So you can learn it earlier than that, obviously from other sources. You might find it on Khan Academy. It's basically what happens when you graph a polynomial. And so, for example, if you wanted to look at where is y greater than x minus 3x plus 2, where does that happen? You know it's a parabola, and you know that those are the roots, 3 and negative 2. You know that because if you set it to y equals, and you let y be 0, if you did that, then when would y be 0? It would be 0 when x was 3 and x was negative 2. By the way, this is why we say that roots, solutions, x-intercepts, zeros, those are generally all meaning the same thing. It's the solutions of this equation. It's called a 0 because y equals 0. When y equals 0 on a graph, you're crossing the x-axis, which is why it's an x-intercept. And it's the roots are also the same thing where it crosses the x-axis. So then, if we were to graph this right here, and you went to negative 2 and positive 3, you would get a parabola that does this. And the 0 would be halfway in between, about right at, if this is 1, it'd probably be happening at about the halfway mark, the half point, right? It's symmetric about that axis of symmetry there. Okay, but the point is, we could tell where is it above the x-axis because it would do it right here and right here. We could do this if we didn't even have the y-axis, meaning I could put this as negative 2 and 1, 2, 3, and 0. So again, you're going to have negative 2, 0, 3. It doesn't really matter. The half right there is where it's going to be. You don't care how low or high it goes. Does the vertex's y value affect whether it's above or below the x-axis? When we say that y is greater than 0, we mean that it's above the x-axis because that's when y was 0. So you're going to have that when x is less than -2 or x is greater than 3. Okay, so either one of those intervals would accomplish that. What would happen if I made it 3 intervals, like y greater than x minus 3, x plus 2, x minus 5? Do I need the y-axis for this? Do I care how high or low it goes? I do not. I can graph all of these on a number line. I don't even need to put the other hash marks. I can just put where they are occurring: -2, 3, and 5. And for a cubic function, which is what you're looking at, it's going to look like this as long as my leading coefficient is positive. And it will be when you expand this. You're just going to get x times x times x, which is x cubed. So it won't matter. That's a positive first term. So then it's going to look like this. Had it been negative, it would just go like this. Again, all of this is like an entire chapter in Algebra 2 or pre-calculus. Graph analysis, similar name. Okay. So now if you were to graph this, you don't care. You're going like this and you're visualizing where you're crossing the x-axis. So it goes like this. Now, I might not know the height right here with the current tools we're using or the depth right here, but that's irrelevant. We only want to know in this problem where it is positive p of x, which means positive y value, which means greater than 0. Okay, let's clear all of this off the screen. And let's give another key piece of information you're going to need to do this problem. If you had something like x minus 1 times x minus 2 squared, what is this as a polynomial? This is a cubic polynomial, and it's going to do exactly what we said about this graph. But because you have an even power, it's not going to pass through the x-axis at that point. Instead, it will hit and bounce off the x-axis. And that will happen every time there's an even power. Again, do I need the y-axis? No, I don't care how high or low it goes for our purposes. We're not graphing an entire graph. We just want to know whether it's above or below or on the x-axis. So I can put a point at 1 and 2. Your graph is going to be going through the 1 and bounce off the 2 and go like this. And this is true whenever the exponent is even. So whenever the exponent is even. Okay, having all of that in mind, a student who is trained and aware of all of these things is immediately going to process that when they look at this. So maybe they might not get, when I solved the problem in my live solve on the AMC12, I didn't at first notice the 2 and the 10, but I did know what the game was. The game was we're graphing things on an x-axis. We've got 10 zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And if they didn't have powers of 2 and 3 and so on, if they didn't have that, then it would just go like this, until it passed through or whatever. There's actually, and if it had been one root for all of them, like x minus 1 times x minus 2 times x minus 3, it would actually not end going opposite directions. It would end going the same direction, and technically it would look like this. And then you'd go up at the end and up at the end, okay? But because that doesn't make any sense, we have to have more intervals or whatever else. You kind of glance back, whatever, it might make sense, but you need to look back here and see this too. And when you notice that it's actually the second power, you realize it's not what you thought. So now what we want to know is, what is the degree of our polynomial? If it's odd, it will end going opposite directions. If it's even, it will end going the same direction. Again, several chapters in a pre-calculus textbook will teach this to you. It's not just one section or one concept. It's many concepts wrapped up into it. So I need to know how many powers I have. And all it is the sum of these exponents of the terms, the binomials that we're looking at. So if I add 1 plus 2 plus 3 plus all the way to 10, as you might have seen earlier, the sum of the numbers from 1 to n is n times n plus 1 over 2. Again, it's a small notebook concept. It comes up all the time on the test. So then you're going to take that 10, plug it in. You're going to get 10 times 11 over 2, which is, of course, 55. Okay, great. So there's 55 powers. Our degree is 55. We will end going opposite directions. Once we know that, we're just going to draw that x-axis and put 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Now, do you have to write all of them? No. You could even just write some. Like I would probably just write the ones where it's hitting up the 2, the 4, the 6, the 8, and the 10. It takes extra time to put all those numbers, and it's a timed test. So you're going to pass through 1, bounce off at 2, pass through 3, bounce off at 4, through 5, bounce, through, bounce, through, bounce. And so you get this one right here is above. What is this meaning of disjoint open intervals? They're not connected. They're open intervals because we don't include 1 and we don't include 2. Because why? You're removing the roots. They're removed from the real number line. And so you're going to get these kinds of values. If you want to look at it as, okay, you have a open dot at 1, open dot at 2, open dot at 3, and so on. So 1, 2, 3, and so on. But on how many of these intervals is P of X positive? So from 1 to 2, is it positive? Yes, because it's above the x-axis. We have to understand what it means for a graph to be positive. It means that the graph is above the x-axis. So you get 2, 3, 4, 5, and a lot of people might have missed this one, but there's one more over here. That would also be a way to make a mistake because you're looking at these kind of semicircular looking things. They're parabolic more so. And you might go, oh, well, that one's not parabolic, so your brain doesn't catch it, and you put 5. That's why you want to be careful at the end. As soon as you draw your final conclusion about something, or semi-final, I guess you could say, challenge it. Think about why it might be wrong. Am I missing anything? And when you do so, you'll go, wait, this last interval that it creates, what about the interval on the other side of 1 then? Was there 1 there? You should be asking. Nope, it's negative there. So you don't get an interval there from negative infinity to 1, but you do get one from 10 to infinity. And that's why the answer will be 6. That's it for this one. Hope you enjoyed it. Let's get to the next problem. All right, let's get a look at this 2023 10B problem 13 and 12B problem 9. If you watched my live solve of the 12B, it's available on my channel. I struggled a lot with this question, even though I recognized a lot of the underlying kinds of ideas that went into it. For example, we might know from small notebook, you should have written down that A times the absolute value of X plus B times the absolute value of Y equals C. These are diamond graphs. It's a diamond graph. And if I make that into a negative sign, it will open it like this instead. And there's a whole bunch of these kinds of ideas at play. And it also kind of reminds me like what would happen if I had this as less than or equal to C is you would shade inside of it. Okay. You might also be thinking of a related topic, like it seems related, of like x minus 1 squared plus y minus 1 squared equals 1. This would be a circle centered at 1, 1. You would shift right 1 and up 1, and you'd have a circle. Does this do that? Not quite. Although I am curious to try what would happen if I replace the absolute value of X with A and B, and I made an A-B chart. So it was like this plus the absolute value of B minus 1 less than or equal to 1. I wonder if I could shift that 1 left, 1 right. I have to think about it, what it might look like. And I thought about trying to create 2 conditions. The first condition would be that this is true, and then we'd have to take the absolute value of A and B. And I thought about trying to do some kind of fun solve that way later on as well. And maybe I'll play around with that later and kind of see how it works out. But for now, I'm just going to go through the solve process that I used with a little bit more explanation. I'm not going to try to go down the false paths that I took in the live solve. I wasted a good chunk of time on this question, and I probably should have skipped it because it just wasn't that simple to do. But I'm just going to use standard knowledge about absolute value of a difference. So this is a small notebook concept. If you have a difference of terms and an absolute value, it will be equal to a piecewise function, essentially, where it's just what you see inside if A is greater than or equal to B. But it reverses the order if A is less than B. And technically, the equal sign could go on either one. It doesn't really matter. It's not going to affect anything if they were equal to each other. If A was equal to B, they would both give you 0. The upper and lower one would. So an example of why you can switch this is imagine that you have 4 minus 7 in the absolute value. Isn't that just 7 minus 4? If I wanted to write it that way, yeah, you reverse the order, right? So we're going to use that concept here. Let's erase this part of it here, and let's just go ahead and kind of think about what's going on. However, our A is really like the absolute value of X. So we're going to have some conditions. Is the absolute value of X, condition number 1, I say that it's greater than 1. And in addition, the absolute value of Y is greater than 1. So if those things are true, then what will happen? If that happens, I don't need the outer absolute value here, here, and here. I could just take it off. And so I would then have a new equation that says absolute value of X minus 1 plus absolute value of Y minus 1 is less than or equal to 1. That would give absolute value of X plus absolute value of Y less than or equal to 3. So we're going to be operating within that if X is more than 1 or less than negative 1, basically is what you're saying right here. And same thing for Y. And I kind of started that way. And then I said, it's kind of hard to say exactly what is going on with that. So I went ahead and did something else. I said, instead of doing that, instead of focusing on that, what if I picked a value of X that was between negative 1 and 1? And I made that my new criteria. So I focused on X rather than the absolute value of X. I said that X is greater than negative 1 or equal to it and less than or equal to positive 1. So I want to make a graph to kind of show what I was doing then. And I went ahead and made the graph here. You don't get graph paper anymore on the AMCs. And so you're going to go 1, negative 1, 1, 1, and draw this graph. Essentially, I'm going to make it so that we're inside this box. Okay, we're inside this box, which means Y is also under these same criteria. They're both between negative 1 and 1. Now, if that happened, the 1 here would actually be bigger. It would be like the second condition where A was less than B. And so it's going to come out positive, but it's going to be less than 1, right? So you would switch the order. This would give 1 minus the absolute value of X plus 1 minus the absolute value of Y less than or equal to 1. And then I'm going to take the absolute values that are there and we're going to move them to the right side. So I'm going to get absolute value of X plus absolute value of Y greater than or equal to, because they went to this side. The one that was already on that side, I'm going to send back to the other side as well. And so you had 1 plus 1 is 2. And now you're going to subtract that 1 and you're going to have 1. This is now looking like that diamond graph that we talked about. So the diamond graph, you're going to say, I'm going to connect here to here to here to here. They're all going to end up being 1. To get those values, the corners of the diamond graph, you can simply let X equal 0. And what will Y be? Plus or minus 1, vice versa. Once you find those 4 corners of the diamond, you're just going to connect them like this. And I need them to be greater than or equal to 1, which means you will be outside of the diamond, okay? Outside of the diamond. But you have to stay in that little inner square. So we shade this, 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 and this. And we currently have an area of 2. Each of those are a half of a square, if you will, half of a unit square. Okay, so then I said, well, what if I kind of extend it out like a dotted line, like a field goal post, I called it. And so I'm going to keep my X value. I'm going to keep my X value between negative 1 and 1. but my y value is now going to be allowed to escape. So now I'm going to say y is greater than 1 or y is less than -1. I'm just giving myself constraints that will allow me to remove the absolute values because that makes it less complicated. Whenever you can reduce complexity, it allows you to think about it and not have your brain hurt as much. So we then say, all right, if I'm going to be up kind of above that box that we currently have, the shaded box with the square in the middle that looks like a diamond, I'm going to be above it right now. So meaning y is greater than 1. So now if that happens, what will that look like? Well, the x one is still going to switch because you're still between there for the x. You're going to get 1 minus the absolute value of x and plus, where's the other absolute value? We take it away because we already know the result based on this knowledge. Then the other one's going to be absolute value of y minus 1. Why is it that? Because the y is more than 1, which means when I take the absolute value, it will still be bigger than 1, and I don't need the absolute value. So now at this point, we have less than or equal to 1, and I'm going to take the 1 and the minus 1, and they're going to cancel. I'm going to reorient it so that the y is written first, and we're less than or equal to 1. Again, try graphing it without the less than or equal to and just make it equal to. Try testing out numbers for y and x on this. What you're going to get is, again, a diamond graph. But we know that your diamond graph is not a diamond graph, sorry. It's like the diamond graph facing this way, but it's, in my opinion, I like a visual representation. It's like you cut it right here, and you grabbed this dot right here, and you folded it up that way. And you grabbed this dot and folded it up that way. So that now your graph's going to face the opposite direction, like this. And now that it's not tied to the bottom of the graph, it gets to what I call escape. I use a very similar visual for the thought process of connecting an ellipse to a hyperbolous graph. And this end's going to go like this. That's going to be the green graph that you're looking at. That's what we're going to have graphed. We can start right here, and we will go same exact slope, just like this, just like that, just like here, and just like here. Okay. Now, if I come outside, does the graph go outside? Sure, it does. But we gave it constraints. The graph would have, if I didn't have any constraints, it would definitely go outside of it. But because it does have constraints, we are staying in there. So where are all the parts in there that would be shaded? Now we want less than or equal to 1. If you were less than for the graph over here on the cheap one, we would shade in here. So we kind of want to shade in that region, but within the constraints of our problem. That's going to add this right here, and this right here, and this right here, and this right here. You also get to pick up a little bit of speed right here if you recognize that x and y have to be symmetric. Essentially meaning they're the exact same situation. X doesn't have some advantage over the y or y an advantage over the x. Therefore, what this looks like in between the field goal posts for x, you're going to have the same thing between the field goal posts for y. If I extend it out this way, where y is now between the red lines, but x is allowed to escape its dark field goal post lines, then it's going to do the same thing. You're going to have x would go this way, and this way, and this way, and this way, and you would shade these little pieces right here. From there, we're going to go ahead and say, all right, well, what if we did x is more than 1 or less than -1, so essentially escaped? That would be the one that looked like this originally. And now we can come back to it and graph the actual diamond graph here, but we have to be careful about what it looks like. Let's use a color purple, and we'll come out, this would be 2, this would be 3, this would be 2, this would be 3, and you're going to connect from 3 to 3, passing right through that dot like that,
It'll pass through those corners to there. It will pass through those corners to there, and it will pass through those corners to there. Again, 2, 3, 2, 3 at 3 units. From that point, we are going to do what? You have to be shading inside of the diamond because it's less than or equal to, but within the constraints that x is greater than 1 or x is less than -1 and y is greater than 1 or y is less than -1. Well, if you try to do it right, I'm going to put this kind of shaded right now. If you try to shade in here, both constraints have to be true, meaning I have to have this true and this true. That's what the constrictions that we made right here. We constrained it. So the purple shaded square down there is not allowed because it doesn't have y greater than 1 or less than -1. So we're going to use the undo button here and get rid of that. In fact, all of those regions here, 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 and there are all going to be off limits. The only one that would work is this little piece right here. You're outside of those field goalposts on both the X and Y, and you will gain these 4 triangles. Every set of 4 triangles is a value of 2 in the area, because if you put 2 of them together, they make a square of 1. So you've got the 4 purple, you've got the 4 red, you've got the 4 black, and you've got the 4 green. The total is 8. Obviously, you don't have access to colored. Maybe you could actually. You could do it on your paper. You know, you could bring colored pencils if you want. You don't really need them. This just illustrates what I'm talking about easier on screen. So the answer ends up being 8. Hope you enjoyed the solution. I will see you in the next video.
Okay, so for this one, 2023 AMC10 B problem 14, we are going to solve it in a couple different ways. And the first way would be kind of the way that I did it when I was solving it on my own. And the second way is a more efficient way that other members of the community had come up with. And I thought about doing that, but I couldn't think about how to get past a certain point. And we'll discuss that when we get to it. The way that I did it is not perfect. It's going to have some issues, but it does rely on a different technique. And the technique would be, how many ordered pairs of integers mn satisfy this equation? And the technique is where you treat one of the variables as a constant, even though it's not a constant. And so if we do that, we might be able to say, okay, let's let m squared be the variable and n be the variable and n equal a constant, even though it's not a constant. Okay, just pretend for a minute. And this does work on some problems. You can see this technique in other contests as well. So I thought maybe it was at play here. And so I'm going to move over the m squared n squared plus mn plus n squared. And now it's a quadratic in m when n is treated as a constant. And so if I factor out the m squared, I will get 1 minus n squared plus mn plus n squared. And so we're just going to do quadratic formula now to see what happens. So if we try that, we're going to get negative b, which is negative n, plus or minus the square root of b squared, which is n squared minus 4a is now 1 minus n squared, and c is n squared. I'm just going to simplify that right now, and we're going to get negative n plus or minus the square root of n squared. It's going to be minus 4n squared and then plus 4n to the 4th. Okay, and then all of that will be over to a, which in this case is 1 minus n squared. Okay, so now from here, if I simplify the inside a little bit further, we're going to see that it's 4n to the 4th minus 3n squared over 2 times 1 minus n squared. And there is options here at this point. You could take the n squared and factor it out as an absolute value of n. So you would get negative n plus or minus absolute value of n square root of 4n squared minus 3. You don't really need to do that because there's an issue regardless of which. The goal here is that if m is going to be an integer, because we want integer solutions, right? Ordered pairs of integers mn, then the discriminant is going to have to equal a perfect square when n is an integer simultaneously. So if you think about this, what we're saying then is that 4n squared minus 3 equals a perfect square. I'll just draw a square to represent a perfect square. In fact, we could say it's a perfect square minus 3 needs to equal a perfect square. And you might remember another problem on one of the two tests this year, and it's also somewhat of a known fact, that the difference in consecutive squares is the sum of their bases. Well, there's only two squares that even have a difference that would be equal to 3. And that's going to be 2 squared and 1 squared, right? So 4 and 1 have a difference of the sum of their bases, 1 and 2. That's the difference in those. If you go up to the next perfect square, the difference is 5. So why is 4n squared a perfect square? Because it is. N squared is an integer, and it's squared, and 4 is a perfect square, so 4n squared is a perfect square. So therefore, the only way that this inside part could work is if n is equal to plus or minus 1. Let me say, okay. And you can actually still work with this, but there's an issue with what's happening. If I try to plug those into here, you're going to get 0 in the denominator, which is kind of an issue. But you shouldn't give up on the idea just yet. Instead, what you might do is go right back to your original equation and plug in n is 1 and see what happens. If you do that, you will get m squared plus m plus 1 equals 1. Equals m squared, actually, sorry. Equals m squared. So at this point, the m squareds will just cancel. And you're going to get m equals negative 1. So when n was 1, we got negative 1 for n. Like this. Okay? Now, the thing is about this, look at the variables in the original expression. They're essentially symmetric, meaning whenever a solution works for one of them and the other one also, like this ordered pair right here, then the reverse must also work, because there's nothing defining about m and n in this problem. They both have a product. They both have an individual m squared, and they have an individual n squared, and they both have a product of them squared on the other side. So if it works for one, you have to be able to switch it, and the other point would also have to work, 1, negative 1. And if you didn't think of that, that's fine. It's not that much time to come over here and actually plug in to n now the value of negative 1. And that's going to give you m squared minus m, because it's negative 1 times m, plus 1 equals negative 1 squared is 1 times m squared. The m squareds cancel, and now you will get m equals positive 1. So it's really not that big of a deal if you didn't think about the symmetric aspect. But that's only going to give us those two. You can also, by inspection, at a glance, you might notice another thing that could work in this version is n equals 0, because that would give you a square root of 0. And so you could have negative 0 plus or minus 0 over 2, which really is just 0. And so again, if it worked for n, you can plug it in, and you're going to get m squared plus 0 equals 0. And then you would get that m also must be 0. And you can actually just look at a glance. They can call that by inspection. You can see that 0, 0 is going to be a solution to this. And so those are going to be your 3 solutions. It doesn't feel comfortable when you plug this in and get 0 there. Probably the reason why it's happening is that you're negating the quadratic when you do that. Like when I come back right here to this first term and I plug 1 in, the quadratic goes away. And so there might be something like that going on. I'm not quite sure how you would explain why that happens off the top of my head. But this is, again, not a comfortable solve. It worked. It generates the correct answer, but the answer being 3 ordered pairs. But there's a better way. Let's look at the better way now. And the reason that I showed this first way is I want you to understand that you're not always going to think of the best, most efficient, and perfectly, satisfactory, confident conclusion method, but you can still survive on those problems by just, trying things out that you might have thought of as well. So now let's go ahead and look at what's going to happen if we instead look at this first expression here. And I thought of this too. If you add mn to it, it becomes a perfect square trinomial. It becomes m plus n quantity squared. And the other side, you'll have this and you'll have plus mn because you have to add it to both sides. You can't just randomly add something, right? So at this point, if you look at the right side and you factor out mn, you're going to get mn plus 1. Okay, so now we have this expression on the left that is a perfect square. And here's where you kind of have to step back a little bit and look more abstract at what's going on. Since m and n are both integers, the product of mn will equal an integer, just some integer. We could call it x, for instance. I don't have to see it as two things, just as the number 6 is by itself the number 6, but it could also be 2 times 3. Okay, so then we can just say that this is equal to x times x plus 1. And if you happen to have done that, if you happen to think about that, what you're looking at, you don't have to write this like this, but if you do, it's a little more obvious what you're thinking. The thought process goes, well, this is a product of 2 consecutive integers because x itself is an integer. And since it's the product of 2 consecutive integers and it needs to equal a perfect square because, again, m plus n is an integer. What do we call that? How do we know that that's an integer? It's the closure property. Closure property that the set of integers is closed under addition, and the set of integers is closed under multiplication. So you're going to have that then. And now what? Since it has to be consecutive integers, we might as well just say that the only 2 consecutive integers that work are going to be 0 and 1, or negative 1 and 0. So if you wanted x to take on the role of negative 1, and you put negative 1 there, you'll get the negative 1, 0. That would mean that m times n must equal negative 1, which of course would mean that m is equal to 1 and n equals negative 1, or m equals negative 1 and n equals 1. Those are your 2 options, okay? What you could do again is say that x is 0. And again, since x equals mn, you're going to have 0 equal to mn, which is only possible if one of them is 0. So go ahead and try plugging 0 in to see what happens for m. And again, you'll see that 0 plus 0 plus 0 plus n squared is equal to 0. So of course, that means n itself also must be 0. And so you get all 3 solutions that way as well. You would probably still have to check these to be safe and feel comfortable that you plug them into the original like we did in the other solve process. So that's it for this one. I'm going to stop recording here and I will catch you in the next solution. Okay, and to finish off this final problem in this set of rapid fire, the 2023 AMC10 B problem 15. What is the least positive integer m such that m times all of these factorials is a perfect square? There's actually a couple different ways that you can think about this problem. And I did it my way, and I'll show you that way first. And then I'll show you another way that's about equivalent in value, but also just an interesting way of perceiving it. And I feel like it should be covered. So the way that I did it is I said, well, at the back end of this expression of factorials is 15 factorial times 16 factorial. And if I look at that, that's really 15 factorial times 15 factorial times 16. And so these together are a perfect square, whatever it is, right? And I can do the same thing with 14 factorial and 13 factorial. Peel off the 14 and the 13 factorials will be a perfect square. Now keep in mind this is all a product. So I'm going to have m times 2 Actually, yeah, 16 is the even one because the 2 factorial is just 2. 2 times 4 times 6 times 8 times 10 times 12 times 14 times 16. Notice what I did with this 2. I justified what I thought rather than simply just accept it must be 2 because we're counting them down by evens. Your brain fills in those little pieces of information, and you should be challenging what your brain tells you, because otherwise it's going to slip in information that's just not true, and that's how we make false assumptions and sillies and things like that. So I thought about it and thought, well, why does this one do that? It doesn't have a 1 factorial, and you realize it doesn't matter. It's 2 times 1 by itself. It doesn't need the other 1 factorial because that's 1 anyway. Okay, so at this point, you have all of this and you want it to be a perfect square. I mean, I'm just going to cancel stuff out. Like if I cancel the 16 and the 4, they are a perfect square. If I do 2 times 6, it's 12 times the other 12 is a perfect square. The 14 is going to have a 2 and a 7. The 10 is going to have a 2 and a 5. The 2 and the 8 make 16, another perfect square. When you're multiplying perfect squares, we don't need to find the value because they're a perfect square already. So for instance, if I went square root of 12 squared times 16 squared times another 16, and then, or 16 is not 16 squared, sorry, I guess it's 4 squared, but you basically have 2 16s anyway. I mean, it's an individual perfect square all on its own. If I combine this 16 with the 2 times 8 one, right? So when we do this, we don't actually care what it is. We just know that it's a perfect square. So because you're going to have the 12 is going to pop out and the 16 is going to pop out. So really at this point, what's left? We have a 2, a 5, and a 7 that have not been paired off with anything. Then in order for the whole thing to be a perfect square, m is going to have to take on a copy of each of these values. If it had said perfect cube, then m would have to play a role of 2 squared, 5 squared, and 7 squared, depending on if we had the same exact scenario. But it works the same way for cubes. You need every single power to be a multiple of 3. In this case, you want every single power to be a perfect square, or 2. It could be 4. For instance, if I had a 2 cubed, but we already canceled out all the additional factors that we would have, so there's no point in doing it that way. So then we have this expression, this needs to equal a perfect square. M must be 1 copy of each of the things that are already present because they're primes and they don't have a paired up prime factor. So then M has to equal the product 2 times 5 times 7, which is of course 70. Let's go ahead and look at the other method that somebody had told me about how they thought of it. And I think it's very valid and it's worth thinking about things in more than one way. It gives you more options when you're facing a problem like this of what you might do. So I'm going to clear screen and go back to the beginning. If you think about it, every single one of these factorials, every single one is going to have a 2. How many 2's is that? Well, 15. Right? Because you have 15 terms there, you're going from 2 to 16, there's no 1 involved. So you're going to have a 2 to the 15th. How many 3's will there be? 1 less than that, 3 to the 14th. And how many 4's will there be? There'll be 13 4's, 4 to the 13th. All the way down, what you're going to notice is that your odd numbers, or your odd numbers, are already all perfect squares because they're even. So when you get to 5 to the 12th, that's a perfect square. As long as you have an even exponent on the attached to the base, whether it's prime or not, that will be a perfect square. And so then you're going to say, okay, well, I don't need any of the odd ones. I would just need what's left over when I take off all of the 2's. There's 14 2's, perfect square. This is the extra one. There's nothing for it to go with. 4 is by itself a perfect square. So to any power, it will automatically be a perfect square. So 4 to the 3rd, 4 to the 4th, 4 to the 5th. Yeah, I mean, that just makes sense. 1024, 32 squared. So, yeah, then let's go ahead and see what we'd have left. Again, you're going to have a copy of 4, but there's no need to write it. So you can just not use it, I guess. And 6 is going to have a copy, and 8's going to have a copy, and 10 and 12 and 14. And then, of course, the 16, which we already talked about, is a perfect square by itself. And you, again, play the exact same game. Okay, so if you were interested in seeing the alternative method, I kind of like that. Hopefully you can observe and potentially put that into practice on a similar problem type in the future. That's it for this set of rapid fire, and I will see you in the next video.